Hello students, so in the last video we have worked on the lots relation and change the lots relation to be in 3NF form. But now we have a new functional dependency that tells us that area derives the county name. This new functional dependency 3NF rule doesn't care about this type of functional dependency because we have a non-key attribute or non-prime attribute deriving uh, deriving an prime attribute. So neither 1NF nor 2NF and 3NF cares about this type of functional dependency, the type by which I mean a non-prime attribute deriving a prime attribute. So BCNF comes here to take care of this type of functional dependency because this will create redundancy problems in our database or in our table. So BCNF here comes to solve the problem. So this is this functional dependency is explained here because he is telling us that assume that we have thousands of lots but two counties. Only we have two counties and each county may have many lots. The Marion County, the first county is named Marion, and the Liberty County. Uh, he's telling us that all lot areas that are in Marion County are having the areas 0.5, 0.6, 0.7, 0.8, 0.9, and 1 acres. And all lots in Liberty County have areas from 1.1 till 2.0 acres. So here uh, the area which is 0.5 to 1 tell us that this lot is in Marion, and if we have the area 1.1 till 2.0, then this lot is in Liberty. And from this come the following functional dependency, which is area derives the county name, or the county name depends on the area. So if we go to the last or the final result of the lots relation, the final result is three separate relations. The first one, lots 1a, lots 1b, and lot 2, and every relation is composed of separate columns or attributes. So now because of the new functional dependency, area derives the county name, this relation, which is lots 1a, still in 3NF because 3NF doesn't care about this type of functional dependency. So in order to make lots 1a in BCNF or applies to BCNF, we need to know what BCNF tell us. BCNF tell us that BCNF tell us that a relation can be in BCNF if and only if left side of the functional dependency should be a super key. So R, the relation R is in BCNF if for every non-trivial functional dependency, sorry for stopping the video, but I was coughing. So we say that for a relation to be in BCNF, all functional dependency, a relation scheme R is in BCNF if whenever a functional dependency in the form X derives A holds in R, if we have this functional dependency, then X must be a super key of the relation R. So R is in BCNF if for every non-trivial functional dependency, the left side is a super key. Here is the left side and here is the right side. So all functional dependency must be a super key in order for the relation to be in BCNF. If we go for the new functional dependency, which is area derives the county name, and we look at the lots 1 a relation. We found that the super key are the property ID, so and the county name and the lot number, or any set of attributes that contains these attributes. However, the left side here in this functional dependency is area, which is not a super key. It's a non-key or non-prime, and this breaks the BCNF rule. So in order to convert this relation, which is lots 1a from 3NF to BCNF, we need to decompose or separate both these two attributes into a separate relation or into a new relation. Here I name it as lots 1a x. So sorry, lots 1ay, and we put here the area and the county name, which breaks both attributes, which breaks the BCNF rule, and the remaining I put them in a new relation named lots 1ax, which contains the property ID number, area, and the lot number. So now lots 1ax and lots 1ay are in B, C, and F. So after converting our relation from 1NF, then 2NF, then 3NF, then BCNF, can we say about our relation or about the final result a good relation schema? So to describe a relation schema or as good, it should be at least in 3NF, general or BCNF. So if you convert your relation schema into 3NF or BCNF, then your design is good. You can say about your design good. We have other normalization rules like 5NF and others, but you will be doing more restrictions on your design. So 3NF and BCNF are enough in your design. So if R is in BCNF, then R is also in 3NF. We notice that when converting from 1NF to 2NF, if you are now in 2NF, then actually you are in 1NF, and if you are in 3NF, you achieve all the conditions for 1NF and 2NF. Also, if you are in BCNF, then you achieve all the conditions for 1NF, 2NF, 3NF. Okay, and as a summary, so if you think about each rule as a box, we see that 1NF, inside 1NF we have 2NF, and inside 1NF we have 2NF. Inside the 2NF we have 3NF, and inside 3NF we have the BCNF. So if you are in BCNF, then actually you achieve all the conditions for 3NF, 2NF, and 1NF. So this figure here is as a summary or the relationships between different normal forms. So also to summarize 1NF, 1NF achieves for us the attributes should be in single valued and have atomic domain. And to normalize into 1NF, we should form a new relation for each non-atomic attribute, because if we have a composite attribute, we need to decompose this composite into separate attributes which are single valued and atomic. And to summarize 2NF, 2NF removes some insertion anomalies and deletion anomalies. So 2NF also removes some redundancies, namely what is the name of these redundancies? Redundancies caused by partial dependency on key, because 2NF only cares about functional dependencies where a non-prime attribute depends partially on the primary key or candidate key. So this creates redundancies caused by the partial dependencies here. 3NF removes all insertion anomalies and deletion anomalies that are caused by transitive dependency, because 3NF cares about dependencies that or where a non-key attribute depends on another non-key attribute. In BCNF, it achieves all achieved by 3NF, and BCNF removes all redundancies caused by all functional dependencies. So here we reach till the end of this chapter, normalization. Thank you for watching, and stay tuned in another chapter, and thank you.